Assalamualaikum warahmatullahi wabarakatuh. Uh, Today, our group will be presenting for our group project for ISP 5C8 Fuzzy Logic, which is fuzzy logic based control for water irrigations. Before we start, let me introduce our group mate. For the first one is Hakim Arif bin Muhammad Kamil Arif. Second one is Ilham Mustaqim bin Musa. And third is me myself, Danish Usman bin Sham. And fourth is Ahmad Hazim bin Muhammad Hanafiah. And the fifth is Muhammad Shafiq Muizuddin bin Razali. And now we move to our introduction. Alright, for the first one, project background. Agriculture is vital to Malaysia's economy, providing food security and employment. Water management is a major challenge, including water scarcity, irregular rainfall, and inefficient irrigation systems. Malaysia's tropical climate, with alternating heavy rainfall and drought, impacts crop productions and food security. A fuzzy logic-based automated irrigation system can optimize water delivery by using factors like soil moisture, temperature, and evapotranspiration, reducing overwatering and underwatering. So now we move to problem statement. Water irrigation management is a critical issue affecting agricultural yields in Malaysia. The growing populations and food demand require smart irrigation technologies to optimize water usage. Fuzzy logic system use data, for example, soil moisture, temperature, and humidity for precise water adjustment. Eva- Evapotranspirations, or ET, influenced by factors like rainfall and plant growth stage, determines water loss and irrigation needs. Small-scale farmers lack exposure to advanced technologies, necessitating a solution for sustainability.
Okay, next I will explain about the objective of this project. So the first objective is we want to identify the fuzzy variable, for example like temperature, soil moisture and humidity level to address the environmental uncertainties. And then the second one is we want to develop a fuzzy graph and rule inference system to manage the irrigation needs. Last but not least is we want to create a fuzzy logic based intelligent irrigation system to optimize the water use in the agriculture industry.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Hazim. So I will present my part for this fuzzy project. So for the first one is significant. Um, we want to minimize water usage while meeting crop requirements using fuzzy logic. Provide a user-friendly interface for farmers to monitor and adjust irrigation parameters. And last one is to adapt to dynamic weather conditions, ensuring reliable and efficient irrigation strategies.
So the next is the methodology. Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Hakim Arif. Today I will present about knowledge acquisition. While the knowledge acquisition is a critical aspect of the system, focusing on key environmental factors such as moisture levels, temperature fluctuations, and humidity, which directly affect irrigation efficiency. These parameters, temperature, humidity, evaporation rate, EVA, for measuring moisture levels serve as essential data sources. To obtain accurate information, climatic stations and water measurement system are required to collect real-world environmental data. This data is crucial for analyzing the existing fuzzy system, identifying areas for improvement, and refining fuzzy rules for water distribution. So by continuously adjusting and collaborating with the real world data scenarios, the system is enhanced for better adaptability and accuracy. Meanwhile, experts oversee the designs and validation process to ensure the system meets the agricultural needs effectively. And now, the knowledge representation. Okay, in our fuzzy logic irrigation system, a semantic network can represent the relationship between the input parameters and valve opening decisions. This is the semantic for the agriculture, the impact it has for the economy, which it can lead to employment opportunity, economical growth, and food security. For the notes on the impact sector, can impact to food availability, farmer livelihood, and rural development. This is also the semantic network for the technological for the analyze water quality, for the notes for quality sector, and the notes for methodology sector. And down here we have the semantic network notes for the challenges of the sector and the notes for the fuzzy logical system sector.
So now for the graph representation. So we have four different graphs. So the first one is soil moisture. So basically this graph displays the membership functions for soil moisture ranging from dry to saturated. So the value from 0 to 60 indicate the soil moisture level, which is a key factor in determining the appropriate valve opening for the irrigation. And next, we have the relative humidity graph. So this graph illustrates the membership functions for relative humidity with category like very high, high, etc. So basically it shows how humidity levels are evaluated in the fuzzy logic system to adjust the valve opening. Okay, for the third graph, which is the temperature graph. So basically this graph represents the membership function for the temperature, which the value is categorized into a very cold, normal, and hot. So basically it's help to determine how the temperature influence the system decision making process for the irrigation control. And then the last but not least is the valve opening graph, which is our output. So this graph shows the membership functions for the valve opening ranging from very low to very high. So the value corresponds to the degree of valve opening from 0 to 100%, which indicate how much the valve should open based on the fuzzy logic output.
Next, follow with the inference system. The first step is fuzzification. Fuzzification is the process of converting precise values into fuzzy values, determining the degree of membership in a fuzzy set. Sometimes this involves using the formula for a straight line, y equal to mx plus c. In this formula, y is the degree of membership in the fuzzy set, m is the gradient or slope of the line, x is the cribs input value, c is the y-intercept of the line. So first we go to the sample input 1, which is soil moisture. We set for 44 centibars, and when we do the calculation, we get the result is saturated 1.0. For the relative humidity, we set as 44%, and the result is high 0.5, very high 0.0. And for the temperature, we set for 8 degrees Celsius, and we get the result cold 0.3, very cold 0.2. Next, we go to sample input number 2. Soil moisture we set for 34 centibars, and we get the result adequately wet 0.33 and saturated 0.67. Followed with the relative humidity we set for 34%, and we get the result medium 0.1 and high is 0.4. And then we go for the temperature we set for 22 degrees Celsius, and the result is cold 0.3, normal 0.2. For the last sample input, which is sample input number 3, soil moisture we set for 3 centibars, and we got the result is dry 1.0. For the relative humidity we set for 6%, and the result is medium 0.6. And the last one is for the temperature we set for 48 degrees Celsius, and we got the result by calculation. It is hot 1.0.
So now for the rule evaluation part. So we have applied the fuzzy rule to the sample input that we have mentioned earlier. So this one is the case number one, which is for the sample input number one. So for this input, we evaluate three rules, which is rule number 8, rule number 12, and rule number 22. So for the rule number 8, we got a minimum value is zero point 0.0, so the valve opening is low at zero point 0. And then for the rule number 12, so we got the minimum value is zero point 0.3, so the valve opening is low at zero point 0.3. So for the rule number 22, we have the minimum value is zero point 0.3, so the valve opening is low at zero point 0.3. So from this evaluation, so we can see that the valve opening is consistently to be in low for this input, which with varying degree of uncertainty. So now let's take a look at the sample input number 2, which is case number 2. So for this input, we evaluate two rules, which is rule number 17 and rule number 18. So for the rule number 17, we got the minimum value is zero point 0.2, so the valve opening is medium at zero point 0.2. And for the rule number 18, we got the minimum value is zero point 0.1, so the valve opening is medium at zero point 0.1. So here we can see the valve opening is determined to be medium, but with lower certainty compared to the previous case, which is case number 1. Okay, last but not least is sample input number 3, which is case number 3. So from this input, so we have evaluate one rule, which is rule number 5, and the minimum value that we got is zero point 0.6, so the valve opening is very high at zero point 0.6.
All right, now we move to aggregations. Aggregations is a process of unifications of the output of all rule where we combine the memberships functions of all rule into a single fuzzy set. So basically to do the graph, we must refer to rule evaluations. So how to do that is we refer from the rules. So this one is for the valve opening. So we see the valve opening for the case one is for low. So we focus on the low part and then how to determine the degree of membership. So we see at the rule evaluations. So what is the degree of membership? So we in here is zero point 0.3. So we set it as 0.3. This also same goes for the case 2. By referring rule evaluation in case 2, we see for the degree of memberships and what kind of valve opening is being used for this case. Next is for the case 3. It's also same by referring the rule evaluations in case 3 and which the valve opening is being referred to and which degree of membership is being used.
Okay, Assalamualaikum warahmatullahi wabarakatuh. And my name is Muhammad Shafiq Mazuddin bin Razali. So right now I will present the defuzzification. So defuzzification actually convert the fuzzy output into a precise valve opening percentage. So in this project, we use the centroid method, which is center of gravity for its accuracy and interpretability, making it the most common technique in modern systems. So the centroid method, also called the center of gravity (COG method), calculates the crisp output by finding the center of the area under the aggregate fuzzy set. It is given by the formula crisp output, just like what I add in the slide. Okay, now is the slide for the first sample input, which is for low valve opening. It is sample input. We include three rules, which is rule number 8: if soil moisture is saturated and relative humidity is very high and temperature is very cold, then valve opening is low. And then rule 12, which is if soil moisture is saturated or relative humidity is very high and temperature is cold, then valve opening is low. And lastly, rules 22, if soil moisture is saturated and relative humidity is high and temperature is cold, then valve opening is low. So we apply the crisp output or the centric method of gravity. We apply the defalsification, and then the result will get 30% of valve opening, which is low. So based on the defalsification process, with soil moisture is 44, which is saturated, and relative humidity is 45, which is quite very high, and temperature is 8, which is very cold. So the system set the valve opening to 30%, ensuring minimum water delivery and preventing overwatering. This highlight the effectiveness of the Mamdani fuzzy inference system in adapting irrigation based on real-time conditions. Next is sample 2, which is we use two rules, and the rules are rule 17, which if soil moisture is adequately wet and relative humidity is high and temperature is normal, then valve opening is medium. And lastly is rule 18, if soil moisture is saturated and relative humidity is medium and temperature is cool, then valve opening is medium. So we apply the defalsification, and the result we get 55% of valve opening. So the conclusion for sample input 2, based on the defalsification process, we get soil moisture is 34, which is adequately wet, and relative humidity is 34, which is medium, and the temperature is normal, which is 22. The system set the valve opening to 55%, ensuring balanced water delivery to maintain optimal soil moisture. This highlight the effectiveness. This also highlight the effectiveness of the Mamdani fuzzy inference system in adjusting irrigation based on real-time condition. And the last sample is sample 3, we use rules by, which is if soil moisture is dry and relative humidity is low and temperature is hot, then valve opening is very high. So we apply the defalsification, and we got 90% of valve opening, which is very high for this. And based on that, we include that soil moisture is dry, which is 3, and relative humidity is 6, and the temperature is 48. And then the system set the valve opening to 90%, ensuring maximum water delivery to prevent drought stress. We also highlight the effectiveness of the Mamdani fuzzy inference system in adapting irrigation based on real-time conditions. And thank you, that's all from me.
Hello, Assalamualaikum warahmatullahi wabarakatuh. Today I'm going to begin to present you about the fuzzy logic based irrigation system. Um, so for our project implements a fuzzy logic based irrigation system that automatically adjusts water valve opening based on three environmental factors, which is soil moisture, humidity, temperature. We use in the system the fuzzy rules and the centroid defuzzification method to determine the appropriate valve opening percentage, 0% to 100%. So first we install the required package, which is scKit fuzzy, because the scKit fuzzy is not included in the Python by default, so we must install it manually. Second is we import the necessary libraries, which is the numpy. The numpy handles the mathematical operations and creates a numerical arrays for the fuzzy variables. The ASCII fuzzy, it provides fuzzy logic functions including membership functions, rules, rule definition, and defuzzification. The ASCII fuzzy control, it manages the fuzzy inference system, allowing us to define rules and logic. The IP widgets, it creates an interactive user interface with sliders and buttons for the user input. From the IPython display, it controls display of the Google Colab. So first is we define the fuzzy variable first, which is soil moisture. soil moisture, humidity, and temperature. Next is the output variable, which is valve opening. Okay. Step 2 is we define the membership function before we use them in the rules. So first is soil moisture. The dry, we assign the linguistic term to each input and output. For example, for soil moisture, we have dry, abnormal, adequately wet, and saturate. Same goes to humidity, low, medium, high, and very high. Temperature, very cold, cold, normal, hot. And this is for the input. For the output is valve opening. The names are very low, low, medium, high, and very high. Okay, for the step 3 is we define the 2022 fuzzy rules that we have from the Google project. So first is all of this is from rule 1 until rule 22. All of this. So what this does is we define how different conditions affect the valve opening. For example, if soil moisture is dry and humidity is medium and temperature is hot, then the valve opening is very high. So next step is we run the fuzzy system. The fuzzy system is irrigation control system rules, and irrigation system, which is control system simulation. All of this, we run the system for the other outputs, which is irrigation system input, soil moisture input, irrigation input, relative humidity, and temperature. What this does is it takes user input, soil moisture, humidity, and temperature, and apply fuzzy rules to determine the valve opening. It uses centroid defuzzification to compute the crisp output to exact percentage of the valve opening. Okay, so um, after this, clear output, and then for the interactive display. First, we have the integration and irrigation system output, the soil moisture, relative humidity, temperature. User can implement or put the number that they wish for the input, and then calculated the valve opening result. We have the output of the valve opening. So next is the interactive UI user interface for input and execution. So in the input, I have put the soil moisture, humidity, temperature, the slider. We can slide it to the minimum of 0 to 60 and the temperature -10 to 60. For the run button, I also have created a run button to run the calculation for the fuzzy system, and then the output of the widget system, there is an output. Okay, for the button click, there's a button that we can click for the moisture slider, the humidity, and the temperature, and then the run button. Okay, so enough talk, let's go, let's redo it. So let's say that how valve opening is calculated using the central method. We implement the medium sample input number 2, which is 34 for the soil moisture. When I click enter, it's gonna move. You can still move it like this, but I prefer to use the input put input so that it's easier for me. 34, humidity 34, and then for the temperature is 22. So we can see that the temperature, when I put 22, the slider is going to move until the middle. So that's user interface, easy user interface. So I click the run fuzzy system, and then it's gonna be here. The output is gonna be here. Irrigation system output, soil moisture 34 from the previous output, relative humidity 34, temperature 22. For the calculated valve opening is 55%. Okay. Okay, that is all. So that is all from our group user interface. Thank you. So after all of that, in conclusion, this project demonstrates how a fuzzy logic-based irrigation system optimizes water usage by dynamically adjusting the valve openings based on the temperature, humidity, and soil moisture. By preventing overwatering and underwatering, it enhances the water efficiency, save costs and resources, and boosts the crop fields. As a climate change impacts the agriculture, smart irrigation systems are crucial for sustainability. In the future, advancements such as IoT and AI integration can further improve adaptability and efficiency for the system. So we hope that our project innovates and supports Malaysia's move towards a modern technological driven farming, strengthening food security and agriculture sustainability. Thank you. Bye bye.